Okay, we have something interesting here today. We're looking at 2025, 2024 squared plus 2022, 2023 squared, and we want to know, is this large number going to be prime? Of course, we want no calculators on this. Sometimes I forget to say it, but it's just that the calculator is going to kind of defeat the purpose. You don't want to multiply this out or use a computer or something. This is more about looking if there's an easy way to do it without number crunching and multiplying this whole thing out. So to get started with it, the trouble is, obviously it's hard to deal with large numbers sometimes. And the other thing is, a lot of times it's kind of hard to figure out if something's prime. I mean, it's not too bad for small numbers because you can just do prime factorization. But after a certain point, it starts getting really tedious. And actually, at some point, it's like almost impossible. Probably larger numbers than this, but if it was much bigger numbers, even computers can have a hard time determining if something is prime. So if you had something like this on a math test, obviously there has to be some kind of trick. They're not going to give you a computer, and even with a computer, it might be impossible. So there has to be some kind of easy way. One thing we know is, even though it can be really hard to check for primes, it can be very easy to check for when something is not a prime. Let's just take some kind of, I don't know, I'm just going to make up a random number, right? Something like this. Well, it's very easy to see that this is not prime. We can tell just by looking at the last digit. Anything that ends in a 0 is going to be divisible by 10. So we don't really have to do any work. We can just see that it's composite right away. Similarly, the same kind of thing would be true if we know an even number is never prime unless the whole number was 2. One more case like that would be, of course, last digit is 5. Again, anything ending in 5 is going to be divisible by 5, so that's not going to be prime. So I think those are the ones that you can do just seeing it in like a second. Other ways that could be interesting, let me see if I can do it. What if this, I don't really want that example. Let's do it like this. Let's do this, and let me change this to a 0 right here. Now for this number, you might not see it right away, but this is actually not a prime either. We can do divisibility rules. For things divisible by 3, all the digits need to add up by 3. You can kind of do it in chunks, like 15 is divisible by 3, 0 is divisible by 3, 6 is divisible by 3, 12 is divisible by 3, 3 is divisible by 3. So you could do that. That's a little slower, right? And you could do the same kind of thing for like 7s, 11, 9, there's one for 37. It gets more and more complicated. So you can do divisibility rules, but then at some point it's like, do you know the divisibility rule for 19? But then at some point, do you know the divisibility rule for 17? Do you know the divisibility rule for 43? And so at some point, you're not going to be able to definitely say that it's prime or not prime. You're just going to be able to eliminate smaller values. So then with that kind of information right there, we want to just do the same kind of thing for this. The only difference is we don't have a single large number. Now we're squaring two numbers, and we don't really want to square it out. So there is like an additional step, but all the same kind of principles we can look for. Like the first thing we did, let's not look at the zeros. Let's look at the case where we had an even number. And then going to our problem, we can do the same thing here because we know if you square an even number, you get back an even number. If you square an odd number, you get back an odd number. So this first number we know is going to be even, and this second number is going to be odd. And so a quick look at our rules on this. Odd plus odd would be an even number. Two even numbers is definitely an even number. And even plus odd, of course the order doesn't matter. Odd plus even plus odd, this is going to be odd. So basically we don't know yet, right? Because what we have, the whole number together is going to be odd, and that doesn't exclude anything. Only these first two cases would tell us that it's definitely composite. So that doesn't really help us. The other thing we could use that's a little different is the GCD of these two numbers. Let's take a much smaller example. Let's say we had 3 squared plus 15 squared. Without even multiplying that out, we know that this can't be prime because the GCD of 3 and 15 is going to be 3. The reason this is true, if we assume we have something in the form a squared plus b squared, and we'll call the GCD of a and b d, so we've got some common divisor of a and b where d is not going to be equal to 1, well then we could write out our number that we want just using we can write our A as like d times m, and we can write our B as d times n. But then squaring it out, we get d squared m squared plus d squared n squared. But then we've got a d squared that we can factor out, so we can write this as d squared plus m squared plus n squared. But then this number right here clearly has to be composite. We're multiplying two numbers. We've already said d is not 1. I guess there would need to be some conditions on m and n so that we don't have zeros, or these aren't 1. But assuming that's greater than 1, and we already know this is greater than 1, this needs to be composite. So going back to our a and b values up here, we could take the GCD of that. Now, of course, that's going to be that could be kind of tricky, right? We don't really know what that is without going back to calculators and a bunch of computations. So I wouldn't recommend trying to actually get the GCD, but you could do some easy checks. I mean, the easiest check is what we already did, the even odd. That would be GCD of 2. We already confirmed that that's not true. Although it's a little different than what we checked, because you could have the odd case, right? If this was odd and this was odd, the GCD could still be 1, but the number would altogether would be even, if that makes sense. But anyway, we check 2, we could check other obvious things. We could check 5 and we'd see it right away. You could check 3 just doing that check we did before of adding up the digits. But I can tell you that 3 is not a factor of both these. And of course 5 is not a factor of these. You can keep going looking for a GCD, but I'm just going to tell you there's not a easy GCD of this, less than 10 anyway. So what's something else we could do with this? Well, we could kind of extend it a little bit further beyond just, the basic divisibility rules, what we looked at with 2. And what we could do is start looking at it in terms of modular arithmetic. What I want to do is take the number that we want to check, where this is A and this is B, and we'll just call that n. We don't know if n is prime or composite yet, but that's what we're trying to figure out. But the check I want to do is this over here to the right. If in any case our n value is congruent to 0 mod p, then we know it's composite. Essentially, we've already checked this for 2. Our check on even and odd would tell us if this is 0 mod p. The way we do this is just dividing in different primes into our number, but we don't want to actually divide it out, because again, that's going to be too much work. So I think what I want to do with it next is for my p-value, I want to choose this to be 5. That's a pretty convenient value, because the nice thing about 5 and also 10 is that you only need the last digit. So I think if you could probably do something with 7 or 3 or whatever, but it's going to be a little more complicated. I think this is going to be an easy check. What we can do on our numbers is, of course, we only need the last digit to tell. So for our a value, this is just going to be congruent to 4 mod 5. Because if you divided 5 into it, you can see 4 is the remainder. I mean, it's convenient that we're less than 5, but if you had something that ended in 8, that would be congruent to 3 mod 5, just dividing 5 into it. So we know our a value looks like this, and our b value ends in 3, so that's going to be congruent to 3 mod 5. The way we can define this more generally, if we think about, we'll call some n value, and we'll say this is congruent to plus or minus 1 mod 5. So that's going to be 1 or 4 mod 5. And then we'll do another value, let's call it k. And we'll say k is congruent to plus or minus 2 mod 5. So that's going to be the case, if we're like this one here, where we're ending in 2 or 3. The interesting thing is when you square this value, we can see exactly what's going to happen. You square this out, the plus or minus goes away, and this is always going to be congruent to 1 mod 5. And then k squared, same kind of thing. You square it out, plus or minus goes away, it's always congruent to 4 mod 5. So just with this right here, we can really consider every single case, because we know m squared plus k squared, 4 plus 1, this is going to be 0 mod 5. So this would be the case we want, where we know it's divisible by 5 and it's composite. But we also need to look at just m squared plus m squared for our two numbers. If they're both 1 mod 5, then this ends up being 2. This would be inconclusive. We can't say at this point, 5 doesn't divide it, so it might be prime, it might not. And then one last case, add these together, you get an 8. This is what we did before. 8 mod 5 is going to be congruent to 3 mod 5. And like this right here, it's going to be inconclusive. So with this little table right here, we can just do it on our problem. We can do it with A. And so our A value is going to be like the -1 mod 5, or 4. We square it, it's going to be congruent to 1 mod 5. And then our B value is going to be the other case. It's going to be like this -2. You square it, and it's going to end up being, you square 3, you get 9, and it's going to be 4 mod 5. So all we need to do is just add these together, mod 5. And so for our A squared plus B squared value, we just get that this is congruent to 0 mod 5, which tells us this works. This whole big number here, when you multiply it out, it's going to be divisible by 5. And so we can say it's not prime. This is going to be composite. Okay, so there you go. That's the basic technique for doing these kind of problems on a very large number. Oftentimes, it's just a couple of quick checks on one number, hopefully like just the last digit, and then hopefully you can get an answer from that. Okay, that's it for today. Thanks everyone for watching. Have a good day.